This meeting is being recorded.
Just so you know.
Okay, I think from our side, we can go, we're ready.
Okay, so I'm just going to change the screen.
If you want, I will let them, if they need to do any introduction.
Mike, Jeff?
Yeah, okay. Well, let's get started, folks. Good evening, everyone. I'd like to welcome you to the March meeting of the Stockton Astronomical Society. I hope you all are doing well and in good health. This evening, we have a really interesting set of speakers. I'm going to let Jeff introduce them, and this should be a lot of fun.
Yeah, this is going to be the farthest we've had a Zoom meeting, the South Pole, and I'm quite excited for it. I am going to butcher these names. Jim, would you like to introduce, since you're kind of the mediator, go-between dude?
Yeah, so sure. Let me just give you a little context. So Moreno and he goes by SAS are what we call the winter rovers. So they signed up to spend 13 months at the South Pole, and their main people that were at the pole left a few weeks, well, about a month ago now. And so they won't have any new company until probably around November or so, end of October, November in there. So their job is to, that, as you'll hear, is to keep the IceCube detector up and running. Most of the time, that's not such a difficult job because it's quite robust, but when something's needed, it's very important. And so it's a hugely important job for the IceCube project, and we're very happy to have Moreno and Salas there. So I'm going to turn it over to them.
Thank you, Jim. Thank you. So, hello everyone. My name is Moreno Baricevic. I'm Italian. For the last 25 years, I've been working as system administrator and high-performance computing specialist for the Italian National Research Councils and various international institutions, among which UNESCO, the International Center for Theoretical Physics, and United Nations Development Programs. I worked in all continents and traveled quite a lot for training activities in developing countries. And in 2018, I worked as a winter rover for the Concordia station, the Italian and French research facility on the Antarctic Plateau, taking care of the 12 experiments and permanent observatories in geophysics, so seismology, geomagnetism, physics of the atmosphere, and space weather. And the same for Celas.
So, hi everyone, my name is Celas, Wincelas Marie-Sainte in entirely. I'm French, so I'm the second European fellow here. And staying here for 1 year with Moreno, maintaining IceCube detector. So my background is in electronic engineer, a bit different than Moreno. I also went over twice before on the Crozet Islands, which is in the South Indian Ocean, maintaining some different kind of project in geophysics and in biology, electronics for biology, with a penguin. And I worked at the French and Italian station Concordia also on the high Antarctic Plateau, which is the neighbors, in fact, from South Pole. Also doing like geophysics and a bit of astronomy. I had a different program than Moreno during some exoplanet research. And yeah, I think that's all. So I will give you a few words now about IceCube project. So what you can see here is one, I would call it one of the level of IceCube. So if you would be walking here at South Pole, you would see that a big blue building with the two tubes on the side. This is what we call the ICL, the IceCube laboratory. This is just a glimpse of the project, which is it's the brain of the project, I would say, because this is where we have our servers but just right below, we have all the science going, which will show you just right after. So another level of IceCube is also the fact that it's 14 countries working together with more than 50 institutions from different kind of countries and working in many different kind of science. We also have like a lot of engineers, technicians, researchers, PhD researchers too. Sorry for the noise. Working in different kind of fields such as dark matter research, supernova, black holes. It's kind of diversified. And I was saying that for me, I see IceCube on 3 levels. There's that international collaboration. There's also that small building that we saw just before, and there's everything below in the ice. So usually when we walk here, we see the big other telescopes such as SPT and Bicep, and us, we see that cute building. But in reality, just below the ice, it's a huge civil engineering work that has been done. So what you see in the hexagonal in violet, it's all the surface detectors. So we have detectors, we have sensors on the ice, and we also have sensors below the ice. So we have about 86 strings. So what we call strings, it's ice drilling, in fact, with containing each 60 sensors. So that makes it more than 5,000 sensors below the ice. That was a huge project for 7 years to install this. And the idea of IceCube is to detect indirectly neutrinos. So the way it works, we have those digital optic modules that you can see here. So those sensors are detecting some interaction of neutrinos in the ice directly. And thanks to that, we're able after to map the direction from where it comes from the neutrino. And also we're able to quantify its energy. The idea of the detector is to do some astrophysical research about different kind of objects such as supernova or black holes. So the way it works, I said just before, it's that we have sensor under the ice. So we're interested in high energy neutrinos. So there's different kind of neutrinos that we could be detecting. But for us, in fact, it's high energy neutrinos. We detect about, I would say, 3 to 4, something like this, high energy neutrinos in the month. So it's not a lot, but we detect millions of neutrinos every day. But we're only interested on those high energy neutrinos. And the way we do also to filter those high energy neutrinos, that we use the Earth as a filter. So as we're able to map the direction coming from the neutrinos, we know that some neutrinos can pass the Earth, and that so we try to consider more those one than the others, and knowing the energy that they have, so we're able to classify them as the one we want. Oh, there's noise, it seems.
We need to have others mute so that we're not getting interference. Thanks.
Thank you, Jim. So I was saying that IceCube was and is a huge project in Antarctica. In fact, I do believe it's one of the biggest, I think. And it's not because we're working for it. So it took 7 years to build it. And every string that you saw just on the screen just before here took about 40 hours to drill. And the installation of every string took about 10 hours after we were afraid that it will froze again. So it's an extremely huge civil engineering work. So a brief history about IceCube. IceCube is about more than 30 years, 35 years of history. So it started in 1988 with the first proposal from Madsen and Learn. And some tests have been conducted first at the South Pole and also in Greenland. And we ran a first detector called Amanda, so during 7 years. And as it was well working, it has been extended to IceCube. The first big discovery of IceCube was in 2013 with 2 detection of 2 neutrinos named Bert and Ernie. And we're still continuing, and it's still working super fine today. So Moreno is going to talk a bit more about it today.
So the detector that we have today is healthy, well working. We have an uptime of more than 99%, usually 99.80%, 99.90%. And during the summer, we have a lot of activities going on. We're having upgrades and sometimes we deploy a new string that is going to happen probably next year, hopefully, because most of activities were stopped because of the COVID situation. And so the logistic was heavily impacted. And so everything was stopped for the last 2 years, basically. Most of the DOMs, the sensor are still working. Few died during the deployment because maybe they froze too fast or there was some issue with the electronics. But most of them are still working, are really reliable. The detector is pretty much stable. There's not much activity going on. We are paged maybe 2-3 times a week. So we received call when there is an hardware or a software issue. And we have a few minutes to take care of that, so to answer these calls. And you can see on the right, this is a view of the internal, the data center at ICL. And you can imagine that 5,000 sensors deployed down in the ice. We have a lot of cables together to collect all the data. And we have more than 100 servers collecting the data, processing the data, and sending the data up north. We are collecting a huge amount of data, more than 1 terabyte a day. So we are sending most of this raw data as standard hard drives. During the summer campaign, we have 1 or 2 shipments of hard drive up north. But all the meaningful events are sent in real time with a satellite connection 24/7 to other telescopes around the world that can point and then try to identify the sources. In the summer, you can see on the left, we have some activities outside. And because of the snow accumulation, sometimes it's quite difficult to operate outside. So we have a lot of shoveling too. And most of those activity happen in the summer when the weather is still fine. We have sun 24/7, of course, and the temperature is around -20, -30 Celsius degrees, while in winter we reach -60, -70 Celsius, and operating outside is getting quite difficult. Not much because of the temperature, because of the dryness allow us to work outside quite easily with the equipment we have. But with the wind chill, it's getting really, really difficult. It's really cold. This is a view of the current extension of the detector. In red, you can see the current deployment. In green, you can see what we call the deep core, which is a denser area of sensor for lower energy neutrinos. And in the next year, we are going to expand by at least 8 times the detector. You can see in this next slide the projection for the future. So on the third from the left, you see the current extension of IceCube, which is 1 kilometer cube. And IceCube Gen 2 will be 8 times larger in optical. And the Generation 2 radio is going to be more than 20 kilometers wide, but that is still a work in progress, of course. On the right, instead, you can see the IceCube upgrade, which will be 7 or 8 string that will be deployed in the next couple of years, hopefully. And that will be focused on lower energy neutrinos, while the larger expansion is for higher energy neutrinos. And you can also see up on the top of the slide that we have 3 different generations of sensors. The first one on the left is the one we have deployed right now. So we are detecting light only coming from downward. And the next generation will be a double detector that looks both down and up. And the third type will be all around detection of light. Just to give you a context about where we are operating, usually on the map, you see Antarctica as a white slice at the bottom of the maps, but actually Antarctica is quite large. It's larger than Australia, Europe, and the United States, and is the largest desert of the planet. And we are really, really isolated here. You can see on the bottom left, that is the extension for which we don't have any life form So for more than 1,400 kilometers, we don't have any human being or any life form. Those are more focused or concentrated on the coastline. The closest station to South Pole is Vostok, which is 1,400 kilometers, which is more or less 900 miles, I think. And McMurdo is more or less the same distance. Also, the Argentinian station Belgrano 2 is more or less the same distance. In the middle, there's nothing else like other than ice. Concordia is 1,800 kilometers. We can say neighbors, but neighbors here have a very different meaning from what you may assume. If you want to compare on the right, you see the United States. The point is focused on Madison, Wisconsin. And the first human being would be in Canada, for instance. This is how the Antarctic plateau looks like. There's basically nothing, just ice as far as you can see. Many light effects produced by ice crystal in suspensions. We have the Fata Morgana, which is kind of mirage. We have the halo around the sun. We have different kinds of halo that we can observe here because the sky is usually clean and is wide open. But as I said, it's the widest desert of the planet. So there's nothing as far as you can see. Where is the station? We are at 3,000 meters, more or less above sea level. Of course, the pressure altitude is a little bit higher. So is you see 9,000 feet, but actually we perceive an altitude of 10,000, 11,000 feet because of the atmosphere is thinner at the poles. And we are isolated for 9 months. So there's no way to have any rescue, even in case of emergency. There was one emergency rescue attempted a few years ago, 5 years ago, I think, or something like that. It was for a severe medical emergency. But other than that, we don't have any vehicle or aircraft that can reach us during the winter. So all the activities, all the logistics is focused for the 3 months of summer.
So the way we get here is for all the station is different. So you have to know that what we there's towns in the world that we call gateways. So it's Christchurch, also Punta Arena in South America, or Tasmania, for example, also. So there's 5 in total, one in South Africa and another one in South America. So the way we do for McMurdo and South Pole is that we go through Christchurch in New Zealand. So we take a plane from there and we land after, it depends on the plane we're taking, but it could take from 5 to 7 hours if I'm not mistaken. The plane you see on the top is a C-130 from the National Guards. So that's the one you can take from Christchurch to go to McMurdo if you have the chance to come here. And then after, you have sometimes the chance to have also those ones to go to South Pole. They're usually faster than Basslers and Twin Otters that are provided by a Canadian company. It's also about like 5 to 3 hours, depending on which plane you take from McMurdo to South Pole. So you have to know that one of the funny things, which is not funny for everybody, but I like it, is that you can stay stuck at McMurdo for 1 or 2 weeks because of the weather. So you can enjoy sometimes McMurdo for 1 or 2 weeks, talk with a lot of scientists in different fields, such as biology, for example, or geology. But you can also hike a lot in McMurdo. So McMurdo is nice to stay to. I love South Pole, but I love also McMurdo. So that's the station. It looks like a bit like a Star Wars building. So all the architectures here in Antarctica are a bit special. They usually designed to face the weather. We have a good condition inside, so it's like living in the t-shirt and having just a normal clothes of the city. Outside is different. We have to wear what we call an ECW. So one of the things that buildings are facing here is snow accumulation because of the wind drifting, and also because here we have a little bit more accumulation than the other station because of the snow falling about 30 centimeters. So inside is pretty comfortable. We have a huge gymnasium, we have a weight gym, we have a conference room where we are here, we have a second one there. We have a music room too. We eat all our food together in the galley. where a team is cooking for us. It's also comfortable because we also have a small greenhouse. We are one of the privileged stations in Antarctica to have a greenhouse, and we have good people here taking care of the greenhouse this year. So fruits are coming and vegetables too. And down below, you can see a sauna. I do believe that it's kind of traditional in Antarctic station because many stations do have one, such as Vostok, Concordia, also McMurdo. A few days ago, I had the chance to camp outside, so I put the tent at the ceremonial pool. It's a bit chilly, but it's cool. Outside the station, it's also different, several buildings. So we are the chance to be circled by many scientific experience, such as South Pole Telescope or Bicep 3 from Harvard. So this is just one of the picture I'm presenting here because in fact we have other buildings. We also have the NOAA that is present here on site. And the only touristic attraction, and some people are crossing the word for that, taking plane with the tourist companies here from Canada. So that's the geographic South Pole and the ceremonial South Pole. So the ceremonial South Pole is composed of 12 flags, which are the 12 countries signing the Treaty of Washington. So the treaty protecting Antarctica for peace and science, I think. Yeah. So that's the end of the presentation, and questions are welcome if you want. One of the things I see that just one of the things, we are a bit more people than before. So just before you arrive, we show the outside world. So this is a live camera of the outside world. So you can see at the end there, we have a SPT, so South Pole Telescope. I don't know if you see the mouse. Do you see the mouse? The mouse on my screen?
Yes.
Yes. So you have
Yes.
here Bicep 3 and Bicep array that is here. In fact, if you take, usually we take that travel here, that path here to go to IceCube laboratory, and we turn to left here, and IceCube is somewhere over there on the left. So sorry, we don't have a camera pointing to IceCube. We like privacy. So no, I believe those cameras are for security or for, yeah, just to, in case.
For the skiway.
Yeah, for the skiway. And another one that I can show you is this one, pointing to the station. So IceCube is behind the camera. So we usually walk to there. It takes us about 10 minutes to go there. It's a pretty enjoyable path.
This is Arrow.
This is Arrow. Yeah, it's true. Sorry. This is pretty enjoyable to go there. Those days, like we have a really warm sun, warm just by color, not in temperature. So, but it's really enjoyable. So I wish everybody could live that.
I have a question if I could.
Yeah.
I'm curious what your primary power source is there, especially for like that server room. Do you use a lot of solar power or generators, or how are you powering up everything?
No, unfortunately not. We depend on fuel, basically. So we have a power plant inside the station, and all the power to ICL is provided by the station. And that is going to be an issue, for instance, for the upgrade, because we will need more power, way more power. Right now, ICL is using like 50 kilowatts to keep up all the machines and the sensors up and running. And for the next generation upgrade, we might need twice as much. And also SPT and Bicep and other projects are requiring more power. So in the future, there will be an expansion of the power plant. Right now we have three generators, and we depend on the fuel that is brought here in summer by the Traverse. So a convoy of bulldozer basically bringing here a lot of fuel. And the LC-130s also are bringing fuel with dedicated flights. So we are strictly depending on fuel. And for solar panels, we have light basically only for 3 months. That would not be enough to power on everything, especially during the winter where we don't have any sun. Aeolic sources, so wind turbines are not working really well in winter because the snow, the ice crystals are really small, and they penetrate the structure of the wind turbine, and they just freeze. They don't work. So we are trying to find new technologies to provide power. Of course, nuclear sources are banned from Antarctica. There was a nuclear power plant in McMurdo in the 70s, I think, but it was dismantled because the treaty doesn't allow any nuclear source here. So we still depend on fuel. The only thing we can do to limit the impact that we have here is to use low power consumption devices. And that's what we try to do. So we try to consume the least possible amount of energy, but still we depend on fuel.
Thank you.
There was
yeah, go ahead.
Oh, I was just going to say there was a question in the chat. Do you want to ask whoever put that in?
The chat. Ah,
It's
okay. Yeah, I can answer to the. So only two there. So no, we're not the only two there for the winter. We're 44 people. We should have been diminished in number because of COVID, but in fact, it went pretty well, the selection this year. So with many difficulties, as you can imagine, but it went pretty well. So we 44 person. On those person, there's about 8% for science. And we have a doctor, physician assistant. We also have electrician, plumbers. It's a small spaceship. You have to imagine that the people inside are a small spaceship. Yeah.
Oh, there's someone going out of aeronaut.
Yeah.
You can see those are the two NOAA scientists.
Yeah.
They are coming back to station now. For IceCube, yes, we are the only two winter rovers here. So we are taking care of the detector, the 100 servers, and all the sensors, just the two of us, but we depend on a large amount of people to keep the station up and running. In summer, during this summer, we were 100. And usually I've been told there might be 200, 300 people here in summer doing research, upgrades, both from technical and science facilities. In the whole Antarctica, during the winter, there's no more than 1,000 people in the whole continent.
Jerry, I have a question.
Yeah, go ahead.
It seemed in that earlier slide you showed quite a few countries participating in the IceCube project with quite a few institutions within each of the countries. Is the data collected by the project, is it disseminated separately to all those countries and institutions, or is there a centralized place somewhere where it's processed and analyzed? How does that work?
All the data is sent to Madison, Wisconsin, where we have a large data center that collects all the data, but all the institutions participating in the collaboration can access the data. But because of the satellite link, we sent everything through Denver, where we have the main satellite hub, and from there it's collected to Madison, Wisconsin.
Oh, okay, thank you.
About 10% of the data goes by satellite. So in roughly real time, and then the rest, as Moreno and SAS mentioned, is kept on hard disk and then physically transported back when the planes start flying again.
We're literally sending hard drives.
Boxes and boxes of hard drives.
I'd like to ask a question about the direction of the neutrinos. I'm assuming that if it hits a sensor here and a sensor here, you're getting a direction. It seems like the likeliness of a neutrino hitting a sensor at all is really low, let alone two sensors. So can you explain that a little?
That's why we want to enlarge the detectors, because the chances that a neutrino collide with the particles are really slim. As you probably know, Neutrinos are nearly massless. They don't have any electric charge, so they barely interact with matter. Billions of neutrinos traverse our body every second, and we don't feel anything, and it's really nearly impossible to detect them. So the chances there is that the ice there is crystal clear at that depth. There's no solar light going that deep in the ice. Muons can be stopped by that layer of ice, and for sure other particles are stopped by the planets, but neutrino pass undisturbed through the whole planet. So the chances are that sometimes we have interaction with the bedrock or with the ice around or inside the detectors, and that's why we get only 3 or 4 astrophysical events per month. We have millions of events every day, but those come from muons or other particles that produce light inside of the sensor. And so the largest the detector, the largest the amount, the possibility that we detect something. That's why we want to expand it. But what we see inside the ice is the Cherenkov radiation produced by the charged particles, which are the debris of the collision of neutrinos and the ice crystal, the atoms in the ice crystals. Does that answer your question?
Well, to get a direction, doesn't it have to activate 2 sensors?
Oh, yeah.
Oh, it activates many.
Yeah, so what you see on the picture here, so the colors, you see there's the red line, sorry if I forgot to mention it. The red line is computed after we get the data. So all the spots that you see highlighted are in fact the sensors that turns on when it detects the Cherenkov radiation. So in red is that high energy.
Celas, we're still seeing your webcam. We're not seeing the.
Oh, sorry.
Oh, sorry, we forgot. Sorry.
Changing
Yes,
here.
that one, yeah.
Sorry, I was changing the slides without you saying. Sorry.
Yes, we were sorry. We were mentioning the slides.
Do you
but
see
were
it
not
now?
seeing this.
Yes.
Yeah. So as I was saying, just so the red line you can see here is computed, in fact. So this is after detection. So as you mentioned, and you're right. So to give a direction, you at least need like 2 sensors. But in fact, as you know, there's more than 5,000 sensors here under the ice. So that's the entire detector, like all the sensors are detecting the path of the neutrino. So here you see the colors is all the sensors, in fact, they're sensing the path of the neutrino. So that's how we're able to compute the direction.
Yeah, and maybe I can help. So we are not seeing neutrinos. The neutrinos are invisible. We only see if a neutrino interacts and creates a electrically charged particle, which then produces the light. And so a muon neutrino will produce a muon, which can go many kilometers if it's high energy. And so for the energy range we measure, we see many sensors see light. So we're not looking at individual neutrino interactions where that light is detected. That's from the electrically charged particles producing light that are produced in the interaction.
Yeah, so I figured at any given second, your humongous observatory is going to be hit by trillions of neutrinos. But I take it that when it interacts with the muon, then the muon is the thing that's activating your sensors.
Yeah, so the interaction produces the muon. It doesn't interact with the muon. So that interaction, a muon neutrino will produce a muon that comes out. In that case, the neutrino disappears and a muon is created that travels in the same direction.
Oh, it travels in the same direction. Okay.
Yeah.
And so when you determine the direction, are you able to locate sources, or is that still kind of questionable?
So I think they covered this on one slide. We have one source that we've identified, and that was using what's called multi-messenger astronomy. So if we just see a neutrino, that gives us some information, but not enough to say definitively what that source is. So we sent out an alert, and then other telescopes look in that direction and see if they can find something interesting that may have produced that high energy neutrino. And then the alternate way is we can also look for clustering of neutrinos from one location. So
And so are these sources stellar cores or galactic cores?
yeah, so the one that's been identified was I guess you would characterize it as a galactic core. It was a blazar, right? So a black hole that's pulling in matter and then has a jet that's pointed at the Earth.
We will interrupt you because we're losing satellite in 4 minutes.
Oh, okay. Yeah.
So we lose the entire connection in 4 minutes.
Yes. Okay. So we use let's I can answer the science questions. If you have any more questions about living and working at the pole, now is your chance.
Yeah, I was curious if you're seeing any effects of climate change in the South Pole.
On the plateau, not really. Actually, the ice is still accumulating. But on the coast, yes, we can observe that, especially on the peninsulas. There are a lot of iceberg every year, larger and larger, detaching from the continent. And yes, there we can observe that. And I think for the first time last year, we had a positive temperature above 0 Celsius on the peninsula, way above 0 Celsius. But on the plateau, we have so much ice, it's so cold that we cannot observe any effect from the climate change here.
Very good, thank you.
How's the ozone layer been going lately? The whole.
Not sure we are in a good position for answering that question.
Okay.
But,
well, I'm saying, how big is the hole? Is it shrinking?
It closed, but it reopens periodically because of the chemical reaction in the atmosphere. And so during the winter, I think it closed and opened in the summer, or vice versa. We are not super entitled to answer the question. I know only what people say about it.
Right. Okay.
But it's getting better. We know that.
Okay, so it seems there's no more question.
I'll ask one more question. So you were at Concordia. How's the life at the South Pole compare?
So it's a bit different. Both system of stations are managed different. Here, there's a lot of companies managing. So there's PAE, the program Antarctic, I don't remember, and Leidos, which are managing so people here, we are science. I would say the science people here are more close to the way we work at Concordia Station because it's institutional, it's national, it's directly, there's no companies managing there. So it's also a small, Concordia Station is 12 people winter hovering. Here we have 44. So the dynamic
really
is
crowded here.
So dynamic is different.
Yeah.
But South Pole is way more comfortable. We have a nice gymnasium and everything. I would say it's way more comfortable and but functioning is different. So it's really positively interesting to see two way of functioning of the station. Definitely.
Okay. Well, thanks so much. I really appreciate you getting up early and
thank you for inviting us.
Yes.
Thank you.
Okay.
Yeah, thank you guys.
Thank you very much.
Thank you. Thank
Have a
you.
great happy day. Bye.
Keep warm.
Yeah, and I can answer if there's any science questions. I'm happy to stay on for a bit.
I have a question about the different detectors around the world, like Super Kamiokande. Do different detectors like focus on different energy levels?
Yeah. So we didn't go into a lot of detail about the construction of IceCube, but the most of the sensors are separated by 125 meters horizontally, so bigger, than a soccer field or a football field between, and then vertically, most of them are 17 meters apart. And so it is a kilometer by a kilometer by a kilometer, but only 5,000 light sensors. So
Right.
one of the really counterintuitive things is a 1 cubic kilometer of ice weighs more than all the people in the world, right? And so if you think about all the people in the world, and then you compare that to 5,000, then you get a sense of just how sparsely instrumented this is. So we are able to do that because we are looking at very high energy. We are looking for very high energy neutrinos, and the path of the neutrino or the muon that's created when the neutrino interacts is proportional to its energy. So if you wanted to look at solar so-called solar neutrinos that are produced in the sun from the fusion reactions, those are about 1,000 times lower in energy than the lowest energy neutrino we measure in IceCube. And so like in Super K, or there's one in Canada called Snow Lab, the light sensors, instead of being 17 meters apart vertically and 125 meters horizontally, are literally one right next to each other, right? And the whole tank is maybe on the order of 50 meters in diameter, 100 meters, something like that. So they cannot measure very high energy neutrinos because all they do is see a very short segment of the interaction, right? And then because their volume is relatively small, the number of astrophysical neutrinos that they see is basically insignificant, right? So yeah, the short answer is yes, they are purposely built for different energy ranges.
Okay.
Yeah.
Okay.
I've got a question. So most neutrinos vary in mass, but not by very much. So what we're talking about is the difference of how close to the speed of light they're coming at us, correct?
Yep.
What is that? What's the percentage range? So from the sun, approximately at what speed are these things coming in?
I mean,
to
no. They're what we call ultra relativistic. So out to many decimal places, they're basically going to this at the speed of light. Okay? So the energy relative to their rest mass, right, is, even for the solar neutrinos, is 1 million times their kinetic energy is 1 million times their mass energy.
Right.
Yeah. And so that is what determines what fraction of the speed of light you're going.
Right.
And so, you would have to go a very long distance to see the differences in speed, right?
Right.
Yeah.
Okay. So we're talking like, you said several decimal points just under the speed of light.
Yeah, exactly.
Okay. All right. 99.9995 or 9993 or something like that.
Even more though.
Somewhere. Okay.
Yeah.
I was just trying to get a grasp of that. Yeah.
Yeah. In fact, the neutrinos beat the light like from a supernova because and the reason is the neutrinos can escape and the light rattles around for a while before in a denser medium, right?
Yeah.
So the neutrinos don't actually, if it was a fair race and they both started in empty space at the same time,
right.
then the light would get there slightly ahead, right?
Okay. That's
So
the idea
that-
that a photon generally travels around inside the sun for 1 million years or so before it escapes.
Right,
Exactly, right.
right.
Yeah,
Whereas the neutrino comes flying out.
exactly. Yep.
Can that give you any idea on distances by the change in that, or is when
No,
neutrinos hit versus the,
well, so what it would do is it depends, I guess, on like how well you could model.
okay,
Like
okay,
so for example, you knew very precisely for a supernova,
right,
um, like how long the light rattled around before
gotcha,
the
okay,
density dropped low enough that the light would escape.
okay,
But the supernovas actually do not produce high energy neutrinos. So so we have a trick on how we can detect a supernova, but it has to be relatively close. It would have to be within our galaxy. But it turns out there's so many neutrinos, even though they're at low energy, right? They would interact, produce a flash of light that would only be seen by one light sensor, right?
right,
But there would be so many interactions that would look like the detector went haywire and
mhm,
got very noisy because there would be all these flashes of light, and then it would relax back to its normal rate of seeing light.
right,
So we wouldn't get directional information in that case. We would just know, we would have a way to estimate how many neutrinos we've seen, right? And then
no, there's a supernova somewhere going off close by, or relatively speaking,
yeah, no, it for us, you know, again, the thing is, you need such a large flux in order to get enough
right,
to
that's right,
interact
right,
that it has to be relatively close even within our galaxy
right,
in order for us to see that change.
like Beetlejuice,
Yeah, not quite that good. So, you know, one of the funny things is you have to be careful that you don't say, yes, we can see them, but the result would be like a blast that would wipe out all life on Earth, right? So it isn't.
Beetlejuice is far enough away,
If it was too close, right? It sends out a big enough pulse
right,
that envelops the Earth, and then
right,
we would know otherwise
yeah,
for a moment, right? We would see the neutrinos ahead, right, and go, oh no, but not by much because of that relatively short distance.
right. So most of the ones that those high energy ones we're looking at then are from, like I said, jets from very large galactic cores that are very active, I'm assuming.
So it turns out to be still an open question as
Okay.
to how that works, right? So the kind of the straightforward way that neutrinos would be produced would be the same way we produce neutrino beams to study them on Earth. We accelerate protons and then we slam them into a target. That produces a particle called a pion. The pion decays and then produces neutrinos.
Okay.
And so anytime there's high energy protons or heavier nuclei, the strange thing is it could be interacting either with other matter or actually with light. It will have that interaction I just described and produce a neutrino. So you need to have a source of high energy particles, and then you need to have a dense enough medium that you get those interactions. But if the medium's too dense, then other types of radiation won't get out. And so then you wouldn't know about them. So we are seeing neutrinos, and we're not able to find sources with other type of telescopes yet, right? So that would suggest that they're in this hidden scenario that I just described. And so what was weird was the very first source we saw was actually almost 4 billion light years away. Okay. And then it turned out was very active with producing gamma rays. And usually if it's producing a neutrinos, we wouldn't expect gamma rays to escape because you need enough target material to produce the neutrino. And then the gamma rays can't get out. So we're still trying to understand that mechanism.
Which makes it interesting.
Very interesting, yep.
Got it.
Is there any research going on right now to engineer a different way to detect neutrinos that might be easier?
We are the best neutrino detectors in the world.
Well, I wasn't questioning that in science. But you gotta, one in a quintillion is kind of a small amount.
Exactly. Yeah, no. So, you know, the short answer is there are some other ways, like if you, the issue is the neutrinos, the higher the energy, the easier they are to detect, right? Contrary to other things that the higher the energy, you know, you might think the harder it is to capture. But, you know, we say neutrinos go through everything, but that's not true. As you start to get even up to energies that we measure, the neutrinos can't make it all the way through the Earth, okay? And so, so that's one factor. But the other downside is they get rarer and rarer the higher the energy. So for about every factor of 10 in energy, you get 100 fewer neutrinos, a factor of 100 fewer. Okay, so to measure the very highest energy ones, nobody would give us enough money to make a detector big enough that we would expect to see in a lifetime even one very high energy one. So you have to come up with a way to make a detector that's even sparser, right, than IceCube, so that you could make it 100 times bigger, right, and not cost so much money. And so it turns out there's a mechanism where you can produce a radio signal, and the radio signals will go another factor of 10 times longer than the optical signal goes in the ice. So then you can build a detector by putting radio antennas in the ice, and you don't have to put them down as deep. And so you can build, you know, a detector that's, say, you know, 20 or 30 kilometers on a side, but only putting detectors every kilometer, right? So you can, and they don't have to be as deep. So you can build that kind of detector for tens of millions of dollars, not hundreds of millions. Yeah.
So what energy levels are we talking about? 10 to the 15th eV or so?
Yeah, so our really, if we look hard and measure kind of an ensemble, we can see down to right around 10 GeV, right?
Okay.
Or maybe 5 GeV, so giga electron volts. So as I say, that's kind of on the order of 1,000 times as high as neutrinos that are produced in the sun, in a star, right? In fusion. And then if we want to get good directional, then you're looking more like a factor of 10, at least a factor of 10 higher energy than that. So like 0.1 to 1 TeV. And then the highest energy neutrino we've measured to date is about 10 PeV. So 10 to the 16th. Yeah.
Wow. So what is the energy level that no one will pay you for yet?
Yeah, so believe it or not, so we have measured, not we, but the community, right? Astrophysicists have made giant detectors to measure cosmic rays. Okay? And so they are literally like, 10 kilometers on a side, but they're 2-dimensional, not 3-dimensional. And they've seen many particles with energies of 10 to the 20th, or even maybe almost 10 to the 21st electron volts. Not neutrinos,
Right.
but electrically charged particles.
Product.
So the crazy thing, which is even hard for me to believe, is those particles will interact with light, right? You don't think of photons as being stuff that other things would interact with. And so it turns out that those very high energy particles can only go a finite distance before they would interact with the cosmic microwave background radiation. Okay? And when they do that, they would produce neutrinos. Okay? But how it turns out, it depends on whether those very high energy cosmic rays are a single proton or whether they're a heavier nucleus. And the reason is that's important is the energy kind of gets just broken up equally between all the nucleons. And so instead of getting an interaction that's equivalent to having a single proton, you have to get basically, if you had, say a helium nucleus that had 4 nucleons, 2 protons, 2 neutrons, then you have to have 4 times as high energy for that interaction to occur. Okay? And so that makes it rarer because, as I said, every factor of 10 in energy you go up, you get 100 fewer particles. So most people would say those neutrinos exist. Question is, how many are there? And if they're mostly heavy nuclei, then you, again, would have to build this really giant, even radio detector in order to see a few of those. So that hasn't been done. Those have not been seen yet.
So Antarctica is just a perfect place to build this 3-dimensional array. How deep in the ice total are the detectors, the deepest ones?
Yeah, the deepest ones we have now are 2,450 meters below the surface, and the ice is a little over 2,800 meters thick.
Wow.
And what we know is the ice on the surface moves about 10 or 11 meters a year. And we are quite confident that the ice is pinned on the rock at the bottom. So somewhere between the bottom and the top, the ice is shearing like this.
Mm-hmm.
And if it shears, then we can't keep our cables connected to our sensors. Eventually they would stretch and break. So down to 2,450 meters, the ice is moving as one big chunk. We think we can go maybe even 200 meters deeper. But that's an extrapolation, so we're not 100% sure that that's right. But most likely we can't go any deeper than that, or that shearing would be a problem.
Wow, that's still pretty amazing.
Yeah. And there are, the reason why we're at the South Pole is there is deep ice, but there's also power and, so forth. There are other places in Antarctica that have even deeper ice, but not the infrastructure to support a project like this.
Awesome.
Is the ice just glaciating, gravity feed towards the ocean, And is there a place on the South Pole where it's like maybe at the top of the pile, so it's not going anywhere?
You know, so the short answer is the center, so to speak, is not at the South Pole. So it's coming by the South Pole. It's not starting at the South Pole. So they call those domes, right? Where the ice starts and goes out. And so there's like dome A, dome C, and so forth, right? So, but the South Pole is not a dome. It's a ice sheet that's moving.
So I take it that Europa might be a really good place to put another IceCube.
Sure. Yeah. No, there's you know, there's some other ways that you could potentially build detectors to look for very high energy neutrinos, including ones that look up at the moon and look for neutrinos that interact in the moon and then produce a charged particle that will decay, right? And so, but you know, one of the things they talk about is developing technology to drill, like if you ever did to get to Europa. So we actually have a colleague in Germany that's developed like basically the equivalent of a submersible, but it's a self-contained drilling device that bores down into the ice that you would use like for Europa, or if you wanted to go down into a glacier to do studies on those properties. We you know, the ice, it turns out, is much more complicated than we would like. There are dust layers, so that changes the optical properties with depth. And then it turns out that dust layers over 1,000 meters are tipped by about 50 meters from one side of the detector to another. And then it also turns out that there's some process going on that's aligning crystals or doing something, but the optical properties differ by about a little bit more than 10% in the direction the glacier is moving than perpendicular. Okay. So all those things are more complicated than we would like. We would like the light to just go the same in all directions. So the biggest uncertainty in us reconstructing these neutrino events are the properties of the ice.
And it would seem that as you're drilling for those detectors through ice that is probably millions of years old, that there's opportunity to do other types of science with the ice that's coming out.
Yeah. So it isn't quite that old. The oldest ice, I think, is on the order at down to 2,400 meters, is on the order of maybe 60 or 70,000 years old. There are some ice cores that approach from different places that approach 1,000,000 years. It turns out there's a whole science to this, and the ice at the South Pole, when you get past a certain depth, it becomes what they call disordered, so that the ice, as it's traveling, actually gets mixed, and so it's not necessarily from from one depth. Okay, so well, I'll tell you one of the crazy things is, so because we needed to measure these optical properties, you know, one of the ways we do it is we have LEDs inside those globes that he showed, the digital optical modules, and we can flash those and then measure how long the light and how much light gets to the next light sensor. But the other thing we did is one of our collaborators designed a device to, before we put our instrumentation in, we would lower down all the way to the bottom and then pull back up. And it sent a laser beam out horizontally and then measured how much light came back. Okay. And so, you know, the time that it takes to return tells you how far it went before it scattered. And then how much light came back tells you about the absorption. And so we did that in like, I think 6 different holes across the detector. And we could see small variations in these dust layers and kind of like corrugations. So we have a paper where we claim we can connect those small variations to how fast the wind was blowing when that ice was formed. And so it's one of the few ways that you can potentially measure or have a proxy for wind speed. So we say, yeah, we can tell you how fast the wind was blowing, you know, 40,000 years ago.
It'd be cool. I don't know enough about neutrinos, but it'd be cool if they had a wavelength and there was a medium in which they would travel slower, because then you can make a lens and pull them to a focus and concentrate them and do more neutrinos at a point than you're doing at a place right now.
Yeah. Yeah. So the issue is, of course, every particle does have a wavelength. And the issue is that the wavelength is tiny, like you know, not even like atomic or not even nuclear size, right? It's much smaller than that. So there's, in order to so there are matter effects, right? So as I said, if you get to high enough energy, the neutrinos don't even make it all the way through the Earth. And then the lower energy neutrinos, the probability of them changing from one type to another actually depends on how much matter they go through. So there are matter effects, but there aren't lensing things like you described.
So the wavelengths on the neutrinos, the higher energy one is going to be a shorter wavelength. So like red light is able to travel through the smoke easier than blue light. Is that the same effect with the neutrinos?
Yeah, but again,
same idea, or at least
it's
is that?
Yeah, but the analogy I like to use, right, is so for a neutrino to interact, it has to create what we call its exchange particle, and the neutrino has to create a particle called the W boson, and that's very massive, right? And so it's kind of like if you had no money and you want to stay at expensive hotels. Most of the time they say you cannot stay here, right? But maybe if you asked 1 billion times, they would say, you're the 1,000,000th customer, you can stay for free, right? All right. So, but if you've got $1 billion, or if you've got $10 billion, and it costs, and you want to show everyone that you've got a lot of money, then you can stay at a hotel like that. So the higher and higher the energy of the neutrino, the easier it is for it to create this heavy particle.
Okay.
And so that's
okay, I can understand that.
Yeah, yeah. But it's not a wavelength.
Okay. Okay.
Yeah. Well, they were great questions. I enjoyed talking with you all, and you know, if any others come up, send me an email. Okay.
Well, we are so glad to have you with us tonight. Thank you very much.
That was very fun.
Awesome presentation.
All right.
Awesome.
All right, then we've got some exciting results coming out in the next few months. So look for science.
All
Okay,
right. We'll look for that 1,000th particle
there we go.
interaction.
There we go. Very good. All right. Good night.
All right.
Thank
you.
you. Oh, that was a lot of fun here.
You're on.
Okay, hey, thanks a lot. Okay, folks. Well, one little announcement. Doug wanted me to ask everyone if they would be interested, let's see, for April, having the meeting over there at the Science Center over there at Oak Park. And Doug, you want to go ahead and explain that a little bit more so that people understand the exact.
Okay, so it was brought up, I think, by Tim. What about using the Nature Center at Oak Grove Regional Park? So I checked into it. We don't have a solid commitment yet, but what we do have from the county and others that use the Nature Center is they would love to have us meet at the Nature Center. There's some technical issues that need to be ironed out for the Zoom meeting and so forth in the Nature Center. We're not sure about the quality of the Wi-Fi connection. But basically, before we really delve into this, what we really would like to get from the 18 people that are still left here tonight is a show of hands, so to speak, on would you guys be interested if we did set it up for April? Would you guys show up at Oak Grove? How many of you would? So I would just want to get, actually, I'll tell you what, email Mike and let him know that you would show up at Oak Grove. And what we will do is we will keep working on it and see if we can make this thing happen. If anyone wants to help out with the logistics of it, let me know. But like I said, I think Eric looked at the Wi-Fi capability, and as I said, there's some question about it we've got to figure out, because we've got to be able to do Zoom and meet in person.
How much room is there in there? How many people can go in?
We can fit 50 in there without too much difficulty, maybe a few more here and there. But
it was about a 30-foot by 30-foot room,
right.
And they had already had about 50 or so chairs in the room. They were all set up, but it should be able to hold about 50.
So a charge to get in the gate?
Yeah, that was the other issue. So technically it's $6 per vehicle to park. If no one's at the kiosk, then you are on the honor system for whatever that's worth.
What if there's someone at the kiosk where you're gonna have to pay $6 to get in there?
Yeah, if someone's at the kiosk, then they're gonna be asking everybody $6. So that's a negative.
That's a
But
negative.
yeah, but it's not, I don't think it's a deal killer.
To me it is.
Okay. Well, it might not be to everybody.
I was thinking maybe a possible way around that would be, obviously we would need to have some prior communication with the park, but maybe we could have some sort of a pass in the newsletter or something that you can just show them, print out the newsletter and take it, it'll let you in, but we'll have to talk with the park and maybe work out some kind of a pass system like that. But
Yeah.
that was my initial idea, but I don't know how feasible it is.
Well,
Or
those
maybe,
that want-
or maybe just show something from your phone or something.
But when we tell them that we're a docent with the astronomy club, they let us in. Maybe they would do that for that night also.
Possibility. I can, like I said, I'll talk to Sandy and see what the deal is. She was supposed to call me back on Tuesday, but she's got some health issues and she was out. So as soon as I get information, I'll pass it on to Mike and the rest of the executive committee.
Jerry, have you heard anything from UOP as far as having the lecture hall open for us?
I had a discussion with Dr. Holland, Kieran, just yesterday, and he's a little hesitant. The official COVID management site says large meetings have to have, we have to have proof of testing, and testing has to be on campus. That's a killer. Because yeah, testing is only available during certain daytime hours, basically. For small meetings, just everyone has to be masked. But there's no clarification on what's small and what's large at this point. In the next few weeks, I mean, all kinds of things might change.
Yep.
So
That's
we might
true.
be able to come back late spring or mid-spring, early spring, maybe.
Jerry, for most of us, can I just interrupt for a second? In most places, if you have proof of vaccination and you wear a mask in larger quantities, I think the state's approving that. They're not open to that?
Well, right now, the rule is testing has to be on campus. That's all they accept for people coming, well, yeah, for teachers and students. So the whole idea of outside meetings is still kind of exploratory, I think.
Okay, thanks, Jerry. Okay, so that's a good update. So I guess maybe the other alternative is having it at the park over there, and maybe that will suffice for a while, and we'll see what happens then. So we'll follow through on that.
Or Denny's.
Well, although what we're doing right now isn't that bad, it does work. It just would be fun to get together on that.
I agree.
Okay. Any news from any of the members that want to bring any topics up? It's kind of a quiet time right now. Everyone I've asked doesn't seem to have much of anything going on, including myself.
Actually, I have one little additional thing. I just got a new email from Dom Nucio up in McCollum Hill. He's got an event scheduled for this Saturday night. And if anyone feels like taking a telescope up and helping out, he's, like I said, he's got a public event up in McCollum Hill. So.
Hey, Jeff, you want to give us an update on future programs for April and May?
I'm kind of hoping Jerry's going to be able to pop up a guest speaker from UOP for April. For May, I'm still waiting to hear from Doug and the lady at the Oak Grove Park about whatever the NASA presenter was going to be for that.
Right. That's once again, I'm going to send another email to make sure that we're in the mix. I haven't heard anything from NASA at this point. So hopefully we'll hear something soon.
Okay. And don't we have a date set for our potluck at Oak Grove Park? Remind me of what date that is.
That's May 7th. That is all rolled into one. It's astronomy in the park. It's striking sparks. It's our potluck.
Saturday, May 7th.
Which
And
is astronomy day.
Isn't that also technically our meeting?
Yeah, I think it is actually. Yeah. For May. No.
We might have to do a little discussion on that.
Okay.
Yeah, the exec meeting. But my understanding was that was kind of like our presentation for that month. If I'm wrong, let me know.
I think that's how we were going to do it, but once again, that's up for the executive committee to decide on that.
Excellent program tonight, Jeff. That was awesome.
Yeah, very cool.
Terrific.
Especially cool to think that the detectors are only pointed down. They're only looking at stuff that's coming through, a good portion of the Earth already. They don't care what's coming up from above. That's too hard to see.
They went through you and me before they went to them.
Exactly.
No, I just thought it was really cool that we're going to have a presentation from the South Pole. I'm really glad Jim was with us because he was able to give us the neutrino details. I think he's in Wisconsin.
I believe so.
Yeah, I think it's in Wisconsin, so.
Yeah.
Can you hear me?
Hey,
Yeah,
Tom.
hi.
Yep, we
Hey.
can.
I had a problem with Zoom. I got online at about 2 minutes after 7 and sat for an hour and a half because it said that they're waiting for it to be started.
Huh.
Well, that's probably my fault. I sent out an incorrect, the long invitation, the long information, I think ended up being the EC meeting, not this meeting, but yeah, try to use the short, the whatever it's called, the short URL. That's the easy way to get here.
Paul, just go to the newsletter. Because I wasn't sure where to find it, but I knew I would find it on the newsletter. Go to the newsletter and just click on that one. That was the easiest way to do it.
The tiny
The
URL.
Yeah, the short or tiny URL is tiny.cc/Stockton Astro. That one we try to keep updated properly.
Well, I apologize for that.
Oh, I just wanted to see the program. That's all. But I was here.
We have it. If you miss part of it, we're recording it. We can send you the link to it, Paul, so you can watch it. I have a quick question for Doug. Doug, there was a public event scheduled for the 13th. You had sent out an email with several events.
March
What
13th. Was it March 13th? Hang on a second.
Yes, March 13th. I think is a Sunday.
Yeah. But that's this coming Sunday, isn't it?
I thought that was the
Yes.
12th, the one with Dawn.
No, that was, yeah, Dom Newsium. Hang on, I gotta get out of this, exit full screen, head to my, where is it? There we go.
I essentially though wanted to confirm the date and time for that.
Right, hang on a second. Calendar. No, I don't have it there. Dang.
The email you sent was March 4th at around 2:40 p.m.
Inbox. Sent.
Well, he's doing
March
that, Jeff.
4th.
Jeff, you said there's no ATM this month because you're
Yeah,
washing the floor or something, or?
Well, the first thing was I re-epoxied my floor. The second thing is I'm about to head out of town. And so we'll resume in April. Thank you.
Okay, yeah, Eric, you're right. It does say March 13th, and that's what the last email or the last thing from Dom was he changed it to the 12th.
You
Okay,
changed it. Okay.
he changed it to the 12th.
What time on the 12th?
It'll be at
At
sunset.
Sunset. Okay.
It's just about 6 o'clock. And if you want to go, I can get you Dom's email or phone number. You can just call him direct.
Do we have anybody already scheduled to?
I haven't heard, nobody has answered me back.
Okay.
Actually, I was gonna send another email to Palmer and see if he was, because he's the closest one to that.
Are you planning to be there?
No, I can't. I'm gonna go up to Sonora this weekend.
So have we committed to having?
We
people
haven't
there?
committed anything to resources. I told Dom I could not guarantee any help. That
Okay.
all I'm doing is putting out the call to everybody else. That's all I can do. So, and he's asked me.
Do we have an idea of how many people will be there?
Usually up there's only about a dozen or so people show up.
Okay, so-
Usually.
So one scope would be enough then. Okay.
Yeah, well, he has one scope. It's just like I said.
does,
could
okay.
use- Yeah, it's just it'd be nice if there was another one up there. If you got the time, he'd love to have the help.
Where exactly is it?
It's at the ballpark, which is kind of hard to find. It's near the high school. So the easiest thing to do is to call Dom and talk to him. And then what I did is I used Google Earth satellite view to find it. Because you got to make a left turn off of the road off of 26, I think it is. And you're basically almost doubling it back. And it's so easy, really easy to miss the turnoff to the ballpark. And like I said, I knew I'd gone past it because I'd seen the satellite view. And once you get to the high school, man, you got to look for that hidden left-hand turn. More obvious on the way heading down the hill, the other opposite direction, because you can see it veering off to the right, but you can't see it as you're driving up the hill.
I believe he limits his events to 24 people,
Yeah.
something like that. Because he actually has people make reservations and he gets kind of pushed when they don't show up.
Yeah.
And he does have 3 or 4 people up there that helped him on the first time. I don't know if he still has them available or not.
Yeah, like I said, I don't know. It's kind of catch as catch can.
Well, go ahead and send me like his phone number or email, and
I will. Let's tell you what. I'll text you this evening.
Okay.
And give him a call. He'd be very happy to hear from you.
Okay.
Yeah, like I said, I was going to email Tom Palmer and see if he'd be willing to do it. Actually, is Tom still with us tonight? Let's see here.
He's off now.
He's off. Coward.
No dummy.
Hey, Ed, do you have any update on Sky Mountain you want to share with us, or
No, I haven't heard a thing.
nothing, huh? Okay.
Nope.
All right, well, let's do the door prize tonight, the raffle.
Oh,
Jerry Stewart, how are you tonight?
Quiet.
$5 richer, I bet.
I'm fine. Yeah. I was muted.
This is yours.
Thank you.
You won tonight. Mike bought it, but I'm the official die roller, and you won tonight. Congratulations. I'm going to need you to email me your snail mail address.
Sure.
Do you have my email address?
I think so.
baldjb@comcast.net. So
Okay.
yeah, if you email me your snail mail address, I'll get that to you in the mail.
Okay. Thank you.
Congratulations.
Okay.
Just real quick, I saw sort of a novelty NASA. I'll put it in the chat. NASA has a thing where you can send your name and they'll put it on a flash drive or something, and they'll put it up on one of the next Artemis missions to the moon. If you're interested, you can go go to the website, type in your name, and they'll give you like a little fake boarding pass, and they'll put your name on a flash drive for you if you want. And say you went to the moon.
so I can say bang zoom to the moon, huh?
Yeah.
I'm thinking of Steve Martin in The Jerk, where he got his name in a phone book, and that's where
Yeah,
the shooter
here's
found his
somebody.
name.
I remember that. That's funny.
I'm going. I'll send you guys a postcard when I get there.
All right, ladies and gentlemen, I think that pretty much sums everything up, unless there's any unfinished business here. And I didn't open the meeting, but I guess we should close it. I don't know how technically correct that is, but is there a motion to close? Someone say aye.
So moved.
Okay, second.
I'll second.
All right, all in favor, if you want to go home, say aye.
Aye. Get out of
All
my
in
living
favor,
room.
push the leave button.
All right, good
Thank
night,
you.
people. Thank you. Nice meeting. And
Yeah. Thank you, Jeff. Great meeting, great presentation.
Excellent.
Enjoyed it. Luckier on this one than I feel
you
like on the
can't get them
last
all.
one.
You can't.
Yeah.
I got a question for Doug.
Sure, go ahead.
Okay, I'm trying to figure out where you're talking about. And you said Sonora, And,
I'm heading to Sonora to my mom's house on Sunday. My niece is coming back from Humboldt. So I was supposed to show up for dinner.
oh, okay.
But the Star Party is in McCallamy Hill, which is a little further away.
I know where that is, of course.
Yeah, I know you were. Okay, sir.